All right. Hello, everyone. This is the third workshop of Intro to Competitive Programming track about math. You can follow our slides with this link. Let's get started. So before we go to our workshop portion, we are going to do the raffle. So for each correct solution of the problems on the contest, we gave you one entry to the raffle, and we'll do the raffle right now. So let's see. Okay, Edward, are you here? Great, congratulations. We'll contact you. You remember? Oh, we have the recording. Okay. Sorry. For Amazon gift card, $20. So we'll contact you and stay tuned for the next raffle. Okay.
If you do the problem on the content, every week we'll have a raffle, and then hopefully we'll.
Yeah. The more problems you solve, the more entries you get into the raffle. So the larger your chances are to win. Okay, so as for the workshop portion, today we are going to talk about binary numbers, bitwise operators, modular arithmetic, and also go over some example problems. So let's get started. So at first, I'll encourage everyone to join the contest and open the first problem, and I'll hand it over to Tony.
Yeah, so take half a minute to open up this problem on your web browser. And here's the problem statement. This is a fairly simple, I would say straightforward math problem in method programming. You would encounter the use of this technique a lot, or like this thing a lot. And then I'll give you guys 2 to 3 minutes to read the problem statement and then see if you can come up with some ideas and then like to solve this problem. All right. Hopefully by now you've already read the problem. And let's take a look at a simple test case. Basically, I'm just gonna summarize what the problem says. The problem says this house 18 has 2 dogs, and then each of the dog is either aggressive or calm, depending on the time you visit. And then now, given the time 3 people visit this house, you want to determine whether or not the dogs are aggressive or calm at each of the times. So let's take a look at simple test case 1. The first line tells us the behavior of the dogs, right? The first 2 numbers tell us when the first dog is going to be calm, like how long the first dog is going to be calm for, and how long the first dog is going to be aggressive for, and then how long the first dog is going to be calm for, and then like the cycle continues. And the third number and the fourth number on this first row tells us the behavior of the second dog, and then the second row tells us when each of the each of our loyal civil servants will visit this house. Now, at the bottom, I have this scenario, this situation graphed up in the diagram. So the first dog is aggressive for 2 minutes, and then it comes down for 2 minutes, and then it's aggressive for another 2 minutes. The second dog has a longer cycle of 6 minutes in total, and then it's aggressive for 3 minutes, followed by 3 minutes of calmness. And then I drew the dotted line at each of the slots, indicating when each of the 3 people is gonna visit this house And you notice that the first person, unluckily, well, he shows up and both dogs are aggressive. The second person shows up and then sees one dog is aggressive, so you output one. And then the third person comes, both dogs are calm, therefore none of the dogs are aggressive, and that would be the final output of this problem. Yeah. By now, hopefully, you have noticed that each dog's aggression is periodic. So, for example, in this example, right, the first dog is aggressive for 2 minutes and then calm for 2 minutes, and then aggressive for 2 minutes and then calm for 2 minutes. So within each period, the dog's behavior pattern is the same. And then like the periods keep on happening over and over and over. So the periods before the current period, like if you think about the time spot one person comes to visit this house, the periods before the current period don't really matter. It doesn't really affect the dog's behavior at the current period. So whether or not the dog is aggressive solely depends on the phase within the current period, or like how many minutes passed since the dog started the current period. Now with this observation, we need we basically have the solution in our hand, but like mod operator is what we need to use for this problem. And just by show of hands, how many of you don't know what modular arithmetic is, or like mod is? Oh, it seems like everyone knows modular arithmetic. Well, just as a quick review, I'm going to go over how modular operator works and then how modular arithmetic works. So A% B, or like you read it as A mod B, gives us the remainder of A divided by B. So for example, 6 mod 3 is 0, 7 mod 2 is 1, and 3 mod 5 is 3. And when there's negative numbers, the rules get very funky, and you generally want to avoid using negative numbers in modular arithmetic. And here are some properties of modular operators modular arithmetic in math. We write A congruent to B mod M if A and B have the same remainder modulo M, meaning if A divided by if you divide A and B by M, you get the same remainder. And here are some properties. First of all, modular arithmetic follows reflexivity. So A and A, obviously two of the same number. When you mod M, you get the same number. Symmetry. If A mod M equals B mod M, or A is congruent to B mod M, then B is congruent to A mod M. And finally, transitivity is another useful one. And that is, if A is congruent to B mod M, B is congruent to C mod M, then A and C are congruent mod M. Does anyone have any questions for this? Should I give an example, or is everyone clear with how this works? Okay, given that all of you said you know modular arithmetic, I'm just gonna move on. So for this problem, since the two dogs' behavior are independent, we only need to consider one dog at a time, and then we collect the result in the end and output our answer. Let's just consider for one particular dog. If a person comes at time C, and the dog is aggressive for A minutes before it comes down for B minutes, then one single period is of A plus B minutes length. Like a single period is A plus B minutes long. And then if we want to find the time, so in the current period, we want to remove all the previous periods from the current time, which we can use modular operator to do this. And it would be C mod A plus B. And finally, we can just solve the problem using an easy conditional statement. If C mod A plus B is greater than A, meaning that we've already passed in the current period, we are already past the period of time where the dog is aggressive, then we know the dog is calm. And otherwise, the dog is aggressive. And for this particular problem, you need to worry about one edge case where if C mod A plus B equals 0, meaning that right now you're at like the last minute of the cycle. So in this case, the dog is always calm rather than being aggressive. This might not make this edge case might not make much sense to you, but once you implement the solution and you test it out with a couple examples, you would see that, you would understand that, this edge case is actually quite annoying. And yeah, that's why working through example inputs is important in competitive programming. And at the bottom, I included the C++ implementation for the solution. Feel free to take a look if you want to see how I solve this problem. Yeah. Next up, I'm going to hand it to Ilya to talk about binary and bits.
Okay, before we continue, can everyone please follow this link and take a very short poll about how well you know binary already? Okay, I'll give everyone 1 more minute. So, well, do you know how convert binary to decimal and back? What operations you can do with that? Okay, that looks like about everyone. So it looks like we have a big range. So I'll try to accommodate everyone. So let's get started. So at first, what is a bit? Bit is a value that can be either 0 or 1. Just like in this sentence here, 10 can be interpreted in binary system as 1, 0, which will mean 2. Binary is what machines interpret your programming code as. For example, all the programs you type in C++ or other programming languages will be translated into binary code, and then the hardware will execute the instructions written in binary. So, but at first, let's look at the decimal system, also known as base 10. If you look at number 123, there are many ways to interpret it. But one of the ways to look at it is say that 3 is the lowest order digit. Otherwise, 3 times 10 to the power of 0. 2 is the next order digit, same as 2 times 10 to the power of 1. And 1 is the highest order digit, same as 1 times 10 to the power of 2. If you compute this expression, you'll get 123. Same logic applies to base 2. So if you have a number 101 in binary systems, you can say that the lowest order bit is 1, which is 1 times 2 to the power of 0. Next order bit is 0, 0 times 2 to the power of 1. And the highest order bit is 1 times 2 to the power of 2. And if you compute all these terms, you will get 5, which is representation of 101 in decimal. I already used this term, but I want you to know that here we start counting bits from right to left usually. So here purple one is least significant bit and red one is most significant bit. This knowledge can be expanded to any numerical system. So if you have a number base n, in other words, each digit can take values from 0 to n-1. It can be converted to decimal system by computing this expression, taking a0 times n to the power of 0 plus a1 times n to the power of 1, and so on until the end of the number. At this point, does anyone have any questions how to convert base n or base 2 number into decimal system? Okay, very good. Conversion back from decimal system into binary is a little bit more difficult. To explain it, I'll provide this example. If you have 13 in decimal system, what you will do is you will repeatedly take the remainder of division of this number by 2 and set it as the lowest order bit that is not set yet. And then divide the number by 2 using integer division. So let's see how it works in practice. 13 is odd, so when you divide it by 2, the remainder will be 1. So we set the lowest order bit to the power of 0 as 1. Next, we divide this number by 2 using integer division. So we get number 6, and 6 in this case is even. So the next order bit, which is to the power of 1, will be 0. Then we continue this operation again and again. So can anyone tell me when should we stop? What's the halting condition for this cycle? Yes?
0.
Exactly. So once the quotient equals 0, that means when you compute the sum, you will have 0 times 2 to the power to some power, which will not give you any additional value. So that term will be 0. So you can stop when the quotient equals to 0. So we can continue. 6 is so we divide 6 by 2, we get 3. 3 is odd, so we set to the power of 2 bit as 1. Next, we divide 3 by 2, we get 1. 1 is also odd, so we set to the power of 3 bit as 1 again. And next, when we divide 1 by 2, we get 0, so we stop. So you can check if. So the result we got is 0, 1, 1, 1, 0, 1, 1, 0, 1. And you can actually check that that's number 13. So you can compute 0 times 2 to the power of 4 plus 8 plus 4 plus 0 and plus 1, which is exactly 13. So does anyone have any questions at this point? How to convert binary numbers, decimal numbers into binary? If not, I'll give everyone around 5 minutes to try to compute these examples on paper or anywhere where you take notes, and we'll go over the solutions later. Okay, so let's see the solutions. So these are the correct solutions. Please compare your answers and let me know if you want me to go over any of these solutions. Or if you have questions how we got this result, feel free to ask. Okay, very good. In general, this operation converting decimal to binary is very useful. So given an integer n, we want to convert it into string of its binary representation. Why is it important? This operation appears in a lot of synthetic programming problems, so it's good to know this algorithm so that you don't need to think about it over every time. And it's good to know the implementation, also because there are a lot of other applications for different problems if you modify it a little bit. So let's see C++ code for conversion decimal to binary, and go through it line by line. So this is a function, decimal to binary, that accepts integer number n and returns a string, supposedly of zeros and ones. We assume that the input is non-negative, but you can extend this into negative numbers as well. So next line, we declare string s and initialize it to empty string. We have a special case when n is 0, and if it's 0, we simply return one string with one character, 0. Otherwise, we perform the same operation that I just described when we were converting 13 into binary. So while the number is greater than 0, we'll first find the lowest order bit that we haven't found yet, which is what this line does. It will return 0 or 1. So n modulus 2 will give you either 0 or 1, depending on the remainder of n by division by 2. And then you add char 0, which is some kind of offset that will convert your integer number 0 or 1 into char type 0 or 1. Later on, you will add this character to the string, and after that, you will divide the number by 2 using integer division, and continue that until n becomes 0. Finally, you return the string. Does anyone have any questions about this implementation? Okay, then I have 2 questions for you. First question, why did we have n equals 0 as a special case? Why couldn't we have just loop while while n greater than or equals to 0, and then just have it as a general case? Does anyone want to attempt? Yes? Well, if you have n greater than or equals to 0, then if n is 0, it will still go to the while. So for now, we have a special case. If n equals to 0, then we return something. If n is greater than 0, then we do loop and then return something else. So the question is, why couldn't we just have a loop with condition n greater than or equals to 0 without special case?
It would skip the while loop, so we would return an integer instead of a string, which is invalid.
Or it's no. Well, it will have some kind
No,
of.
it would just return the empty string.
Sorry.
So it would just return like empty string.
Well, not really, because you will still go inside the loop, so it will still add something to the string. So any non-negative n will still enter the loop. Yes? Yes, exactly. So as I said, our halting condition is when n equals to 0. So when the quotient at this line, when n becomes 0, every next line it will still be 0. 0, 0, 0, and then the loop will never exit, because every time you check the condition, n is still greater than or equal to 0, because 0 is greater than or equal to 0. So it will repeat infinite number of times. And yes, your result will be correct because all those higher terms are still 0, but you will never finish. So that's why we need a special case. Okay. Right. That was my question. Any more questions? Okay, then let's continue to our second example problem. Please open problem B on the contest, and I'll give you around 3 minutes to read through the problem statement. Okay, so I hope everyone had a chance to read through the problem statement. So I'll give you a quick summary of the problem statement. So essentially, there is some board and with 2 buttons to type 1 and 0. Every time you press one button, it prints one character. Every time you release that button, so you keep pressing, and then when you release the button, it prints that character again. So you have 2 buttons for 1 and 0, and they print each time when you press and each time when you release. So for now, you might be wondering, why are we talking about 1s and 0s if you are given strings of characters ABC? Well, that's because each character in the input can be converted in the ASCII. So you probably have seen this table from our workshop last week. Essentially, every character that we type can be converted into some ASCII code in decimal, and it also has, and that decimal number also has its representation in binary. So from character as capital, for example, you will get binary representation 01010011, and that's the string that you are typing with your board. Well, and every string consists of many characters. So string is composed of ASCII representation of every character. So if you convert every character into ASCII and then merge them all together, that's the entire string that you need to type. So the task for now, you need to figure out whether after typing the entire string of zeros and ones, at least one of the buttons will be still pressed. So your hand will be pressing it because you, for example, you typed 1 and then you're still pressing it and you didn't release it. So that would mean that one of the hands is trapped. Does anyone have any questions about problem statements, the setup? Okay, if no questions, I'll leave this on the screen and I'll give you guys around 7 minutes to think about how you can, don't code yet. I'll give you some time to think about the solution first. Okay, so hopefully everyone had a chance to think about the problem. Now I'll go over the solution, some hints. Okay, so here is an observation. Our hand will only be trapped if we have pressed down one key without ever releasing it. So let's focus on 0 key, for example. So this will happen if we type in just 1 0 key, our hand is pressing it. If we type 3 times, then we press, release, and press again, so it's trapped, and 5 times, and so on. Essentially, if we type some key odd number of times, it will result in the corresponding hand being trapped. So let's see how it works in an example. If we are typing a string 1001010, it has total number of zeros is 4 and total number of ones is 3. So that means that the hand that is typing once will be trapped because we will press, release, and press again. While for the fours, we'll press, release, and release. So, right, the hand is trapped. Now imagine the next character you're typing is 1000011. Now the total number of zeros is 8 and total number of ones is 6. So both numbers are even. That means that both hands are free. So we type as free as a result. So now let's generalize this idea. What are the steps that we need to do in order to get our solution? First, we convert each character in the string into the string of ASCII, which is done automatically by C++. After that, we'll convert each ASCII value into binary using the conversion that we used from decimal to base 2. And then in the resulting string, we will count the number of zeros and ones. And finally, we need to check if we are trapped or free. And here is my question for you. So how would we check that? And when should this check be done? Does anyone want to answer? After we counted numbers of ones and zeros on the string, what's the condition that our hands are free? Yes? Yes, exactly. So if both numbers are even, then our hands are free. If at least one of the number is odd, then our hands are, at least one of our hands is trapped. And we can check this at the end of every string. So does anyone have any questions about the solution idea? Okay, if no, let's go to implementation. So I have the code starter in this paste bin here, but I'll go over it on the slides as well. So first thing you want to notice in the input specifications is that we are not given just one string, but several strings. So you will perform the same set of operations for each string. So you want to have some kind of while loop And while you can read the string, you read it and then do what you need to do. So in this case, we can use C++ function getLine, which will take the entire string and then you will analyze that string. So this is the code starter that we want to use. So at first, as usual, you declare include statements using namespace std. So this is what you can try to do in your main program. So first thing, we declare our string s that we will use as the input parameter. While we can read string from console using getLine s, we will do the following. So as we said, we want to count the numbers of zeros and ones in the string. So we'll have, let's say, two integer variables, one for zeros and one for ones, and we will initialize them both to 0. Then we'll do some magic and count those numbers, which I'll talk about later. And afterwards, we want to check if we are tree or trap. So if both numbers at the end are even, then we are free, and we print that. If at least one of them is odd, which is elk branch, we type trapped. So what about the code that goes inside there? Right. This is some code that I'll give you pseudocode for, some steps and hints, and I'll ask you to implement it yourself. So looking at that code, again, we have our counters up there, and we want to go through each character of string s. For that, we will use for loop and go through characters of string s one by one. So for each character, we want first to cast it into integer type, which will perform our conversion from character to ASCII value. And this is done automatically. You can just assign it to an integer variable, and C++ will do the conversion for you. So now you have ASCII value, decimal value, into some variable ch. So the next step would be to go through each bit of that value, essentially the binary representation, get the binary representation of that decimal value, and you can simultaneously count the number of zeros and ones that you get. You don't necessarily need the resulting string of zeros and ones, because while you get them, you can actually count their number. You only need the number of zeros and ones. So I have some hints for this step too. So first of all, notice how problem statement mentions that we consider each character as 7-bit value. So even if you have, let's say, some number that's encoded 0000001, you still want to count all the 7 bits and not stop your loop like we did when we get to the first 0, because that's what we actually type. We'll type 6 zeros and 1. So for that reason, you can have some kind of counter and again do a loop, while or for loop, up to you, until it becomes 7. Next hint I have is you can notice that you can check the last bit, just like we did in previous examples, by looking at the remainder of the value modulus true. So if the remainder is 0, then the current bit is 0. If the remainder is 1, then the current bit is 1. And you can update your counters correspondingly. And finally, to go to the next bit, just like we did before, we can use integer division. So simply divide the number by 2. So hopefully this is helpful. And now I will ask you to go to that pastebin link that I had before. And you can copy the entire code there and try to replace the steps comments with code and submit it into Caddis. I'll give you around 10 minutes for that, and then we'll go over the solution. Okay, we are running a little short on time, so we'll continue. Hopefully everyone had a chance to attempt the problem. No worries if you didn't get it your first try. Obviously 10 minutes or whatever number, whatever time is not enough to get it. So let's see what the solution looks like. So essentially, first step, you want to convert if character of the string and into the ASCII value. So you will just say you will just assign some integer variable to s sub I, and it will do the conversion for you. Next, you can have a while or for loop. Here we have while loop. So we have a counter. That means that the while loop here will increment the counter 7 times, and we will get exactly 7 digits. So each time we will see if the remainder of our integer modulus 2 is 1, and if that's the case, we'll increase the number of ones that we have, and if it's 0, then we increase the number of zeros that we have. And then the next line will go to the next bit. So notice how here we don't even use any strings, so we don't actually convert decimal value of ASCII into binary, but we still use the same methodic, the same algorithm that we used when we were converting it. We still check the last, we still check the remainder, and we divide by 2 using integer division. And afterwards, we increment the counter so that we can go through the while loop exactly 7 times. Does anyone have any questions about this snippet of code?
Why 7 in the while?
Yeah, that's a good question. Actually, in the problem statement, so they say that the binary code for each 7-bit ASCII character. So essentially, what they're trying to tell you is when you look at the ASCII table, you don't only need you need the entire binary value. So you need an entire string that encodes it, because when computer reads it, they actually need to be sure that they're reading, that exact character and not maybe several characters together, which just have shorter lengths. So yeah, that's just a problem statement. So we want to take 7 bits. So any more questions? Okay, if no questions, here are some useful links about C++. If you have questions about loops or about how getLine works, please feel free to check out these links. And we'll continue with bitwise operators. And again, I'll ask everyone to follow this link and enter the poll and to tell us how well you know bitwise operators already. I'll give everyone around 1-2 minutes to do that. I'll give everyone 1 more minute to do the poll. Okay, so it looks like there is some distribution, and hopefully after this workshop, you'll get a better understanding about bitwise operators. So first, let's start by introducing a new type in C++ called Boolean. So Boolean is the value that can take one of two values, true or false. And there are some operations that we can do with Booleans. So you might have seen this before. So these tables are called truth tables. So the way you fill it is you take the operator that's at the top leftmost cell. In this case, it's and on the left and or on the right. And then on each intersection of row and column, you put the resulting value of taking that operator between two operands that are in the row and column. So I'll explain how this works. So first, let's look at the table on the left. 2 ampersands denote AND operator. It takes two booleans and gives a result as a boolean. So it works just like in real life. For example, true and true will give you true, and then false and anything else will give you false. So the result is only true when both operands are true. And then for the second table, this is operator OR. So the result is only false when both values are false. And if at least one of the values is true, then the result is true. So for example, true or true will go true, and then false or true or false will all result in true. Does anyone have any questions about how we got this? So you might notice that Booleans are very much similar to bits. They can also take two values, 1 and 0, and true or false in this case. So that intuition is correct. We can actually perform the same operations on bits. If you encode true as 1 and false as 0, you can get the following result. Essentially, you can say that 1 and 1 is 1, 1 and 0, or 0 and 1 is 0, 0 and 0 is 0. So the result is only 1 when both values are 1. And same logic with OR. If at least one of the operands is 1, then you get the result as 1. And if both operands are 0, then the result is 0. Well, for now, we're only working with values that can take, with numbers that can take two values, either true or false or 1 and 0. We can extend this logic for all integer numbers. So for that case, let's first look at AND. There exists an operator called Bitwise and written as a single ampersand operator. In this case, X and Y can be any integer types. And what this operator does, it converts, well, it doesn't convert it literally, but how you can imagine it is that it converts each number into binary and then takes AND value of the bits at each position of both values, and then takes the resulting binary result, binary number, and returns it as integer type. Maybe we can close the window. Okay, so to better understand how it works, let's look at a concrete example. So let's take AND value of X equals 13 and Y equals 11. So the first thing we do, we convert these numbers into binary. And as we've seen before, 13 is 1101 and 11 is, you can check, 1011. So let's start from bit position 4. We see that take AND operator on each column. So we see that 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, and 1 and 1 is 1. So this is the line that we get, and we get 1001, which in decimal representation equals 9. That means that 13 and 11 will result in 9. Does anyone have any questions how we perform this? So essentially, you just translate both numbers into binary and then take the result of corresponding operation column by column. Okay, if no questions, the same logic applies to OR operator. So bitwise operator is denoted as single vertical line, and don't confuse that with two vertical lines. So two vertical lines is the operator that takes only binary values. That takes only binary values that can be 0 or 1. Bitwise OR can take any integer types, and again, the result will be the OR value of the bits at each position in both values. So let's see the example for the same numbers, 13 and 11. Again, we convert them into binary, and then we say 1 or 1, result is 1. 1 or 0, result is 1. Same 0 and 1 is 1, and 1 and 1 is also 1. So we get all ones. That's okay. So the resulting value is 1, 1, 1, 1 in binary, which is 15 in decimal. So 13 or 11 equals 15. Any questions at this point? Well, there are very that's a very good question. So there are very interesting applications to that. Unfortunately, they're a little bit more complex that we will not go over that today, but you can essentially represent sets with binary values. When 1 means that that some element is present in the set, and 0 means that some element is absent in the set. And then if your elements are unique, you can get a single binary number to represent which elements are present in the set and which are not. And then by doing some operations and or, you can, let's say, do the operations of like intersection of two sets, union of two sets, and so on. So that's one of the applications. Yeah, it might not be super obvious, but it's good to know how it works. So when you get to that topic, you can actually use it. Any more questions? Okay, so then I'll ask you to do these 4 computations. Let's take around 3 to 5 minutes to do that, and we'll compare our answers later. Okay, I hope everyone had a chance to attempt, and I know it's not enough time. We're just run a little short on time, so I'll jump straight to the solutions. So these are the final answers, and I want to bring your attention to number 3. So hopefully you didn't convert this horrible number into binary. So all you need to notice is that 1 in decimal is actually a lot of zeros and 1 in binary. So essentially, when you end anything with 0, you will always get 0. And the final bit will just check if the number is even or odd. So in this case, the number is odd, so the last bit is set to 1. So when you end it with 1, you get 1. So that's how you do number 3. Any questions about any other or number 3? Okay, so in this case, there is another operation called XOR, and I will not go over it today. We have slides for it. So I'll encourage all of you to look through the slides, and we have some exercises on XOR. Instead, I'll jump straight to the bonus problem that I announced last workshop called Tetration. So I'll remind everyone the problem statement. Let's take a couple of minutes to read through it. Actually, I'll read it for you. So tetration is a mathematical operation defined as a to the power of a to the power of a, and repeat that n times. And then you, to denote that, you put n on the left of the actual number. So next, we can define infinite tetration as doing the same operation, not n times, but infinite number of times. And that would be a with infinity on the left. So there is a certain range of numbers A that can actually lead to a real finite number. Let's call it n. So the task is, for a given number n, if there exists such A, we want to find it. So last time we gave everyone a hint, asking to try taking natural logarithm of both sides. So I hope you attempted this problem, and if not, I'll guide you through the solution. So there is some interesting observation that if you take only the exponent of the right-hand side, it's still equal to the same right-hand side, right? Because that's still infinity. So if you take infinity minus 1, it will be still infinity. So if you only take this part of the number, topmost, the exponent, it will still be n. So you can replace it in your equation and say n equals a to the power of n. And then that equation is easy to solve. You can simply say a equals to n to the power of 1 over n. And this can be easily implemented in C++ using POV function, which takes the base and exponent and returns value in float or double. Does anyone have any questions about this problem? It's a very nice math trick, and yeah, I like this problem. Okay, if no questions, let's go to the feedback form. So I encourage everyone to fill it out. This time, we will see 2 questions on the form where you can put answers. One is a small question about one of the problems that we did today. And it will ask you to give a short response, 2 sentences. And then the next question will be just some feedback that you have for us. So if you attempt both questions, so the answer for the problem prompt doesn't have to be correct. If you attempt both questions, you'll get bonus entry into the raffle next time, in addition to the number of problems that you solve from the contest. And if you want to be entered to the raffle, please put your name. You don't have to, but for the raffle, please put your name on it. So I'll give everyone around 7 minutes to try it. And it's okay if you don't know the correct answer for the problem prompt. Just attempt your solution.